much, Yang, and it's my great pleasure to give a talk here. So today I'm going to talk about DIP and NIR, which is a very powerful, I would say, a very powerful kind of new tools for solving inverse problem, especially I would say nonlinear inverse problems. And that's going to be my focus today. So this work is joint work with several of my PhD students in the group, and of course with contribution with others in my whole group. So let's start from zero inverse problems. I think this is a mathematical science department, so probably we are familiar with the term inverse problems. So in inverse problems, we have measurement of some object interest. So for visual inverse problem, typically these guys are images or videos or whatever visual objects. So we either we know or maybe partially know the forward process, the observation process. And the goal of solving inverse problems is basically try to reconstruct or try to estimate this inverse mapping from the observation. And there are so many visual inverse problems in computational imaging, computer vision, or in general signal processing or applied math. The low-level problems like image denoising, super resolution, these are already very classic image processing. The whole field of 3D computer vision is about trying to reconstruct 3D objects from multiple images. So that's a big inverse problem, and of course, in 3D vision, people divide that into multiple stages, and each stage is an inverse problem. And for modern medical and scientific applications, we also seen similar inverse problems. For example, MRI reconstruction, this is a very famous medical imaging problem. And to things like a phase retrieval, which is used to imaging small or large-scale projects. Objects. So the traditional method for solving inverse problem has been mostly based on statistical inference and numerical optimization. So again, the inverse problem we are talking about is suppose we observe y, which is generated from fx. F is called a forward model, and x is an object of interest. And the traditional method is basically trying to formulate this into a regularized data fitting problem, where you have a data fitting term, where L is a loss that's measuring how well you can fit the data, and regularization term, which basically encode prior information about the object you are going to recover. But if we think about this general framework, there are a bunch of limitations, or at least there are a bunch of limitations. So it's not clear if I give you a problem, it's not clear which loss you should choose typically, because the loss choice typically is motivated by the noise model we have about the measurement process, but it's not always the case that you know the noise model, or maybe you know the noise model, but actually you can't find a good loss. Maybe you know that the noise process is like a 2 or 3 kind of noises intermingled together. So then it's very hard to find the appropriate loss term. The other situations are the case where you do know some knowledge about the objects, which hopefully can turn into a regularization term. But it's not always the case that you can easily find some mathematical function that you can do appropriate regularization. Although, yes, I mean, over the past decades also, people know that for sparse structures, that we have very good candidate for doing sparse regularization, like one norm or general sparse models with like low rank structure with S structure. But these are very special cases. There are many cases where you do know their structure exists, but it's just very hard to describe, or finding the corresponding regularizer there to describe that kind of phenomenon. And another complaint in practice is about the speed, because once we set up a numerical optimization problem, we need to solve it. And we typically run iterative methods, maybe, I don't know, 100 iterations if you find reasonable good initialization. or maybe 1,000 iterations, so that's not rare. So, if your application touch on real-time, have some real-time constraints, then, you need to really think hard about how to speed these things up. So we all know that deep learning have changed a lot of things over the past decades. Similarly for inverse problems. So there are several families of ideas. I just want to briefly touch on, how people are thinking about inverse problem nowadays. I would say generally there are several lines. The first line is probably the most natural and the most radical way. So this way is that we try to collect large enough training set with the xi and the yi pairs. So basically you have the object and the observation pairs. And basically what you do is that you try to feed data into a neural network. You try to feed in your observation, and hopefully it's going to predict the object of interest. And then you set up your empirical risk minimization problem, just like what we do typically in machine learning. And then you try to solve it. This sounds like very attractive because you basically don't think much about the model itself, the F itself, because there are indeed inverse problems where we don't know much about the forward model F. Okay, so in this kind of situation, it's very attractive. But actually, if you do know something about the F, this is probably a waste of that knowledge because this basically doesn't include anything explicitly into your problem solving process. And another major problem is that how do you make sure you can collect a large scale data set, and how do you make sure it's sufficiently representative of your data distribution? For simple problem like linear inverse problem, this probably is not a big concern because the forward process is linear, and probably still reasonable that you can simulate some data, right? And but once your F become more complicated, where for example it become nonlinear, this problem become harder and harder. So later I'm going to touch on some examples where it's very difficult or challenging to collect sufficient large data set for this kind of approach to be feasible. And another possible problem is that actually this sounds like very natural, and there shouldn't be any problem. But actually, if you carefully think about this, there are problems, especially if this guy is nonlinear. There are problems where this forward model have some symmetries. So what do I mean by that? Just imagine that, for example, let's take a simple example. This forward model is a square function. Okay, so I input a scalar. This forward model is going to take the square of the scalar and give you the squares. Now, if I think about the inverse process, the square, and I'm supposed to give the square root, but square roots, we have the sign symmetries. So strictly speaking, this is not a function. Or if you have to define a function, you can define a function that input a scalar and output a set, right? So when you have this kind of problem, if you just directly throw in the data, actually you are going to face some significant learning barrier, as we discussed in this paper. So the square example, of course, is pretty naive. You may say I can easily fix it by fixing the signs, of course. But when you come to general nonlinear problems, you actually are going to face a lot of these kind of situations where you do have strong symmetries in F. And the object you're going to learn is highly, highly acceleratory. I mean, the function you're going to learn, the F inverse, is highly, highly acceleratory. Then you need to think hard about how do you deal with this kind of learning situation. And then people realize, due to this limitation, people realize probably it's, better we try to encode the information about F itself into the problem solving also. So there are several line ideas in this middle way. Basically, I would say most of the ideas start from the classic regularized data fitting formulation. And the general recipe is basically you try to revamp or try to replace part of the numerical method for solving this operation problem with some neural network. Okay, so the neural net can be either pre-trained or maybe trainable using a large collection of data. So there are several popular ideas. Again, I'm not going to be exhaustive. There are survey papers out there. I'm just going to, highlight some of the key ideas there. One family idea is called algorithm IRO, which basically is based on the observation that, in numerical operation, people typically tend to approach this kind of problem using projected gradient, right? Of course, that's provided this R is sufficiently simple so that you can do easy proximal operation. But anyway, in any case, we are taking some gradient step and then we do a kind of proximal step. So the idea is that, since I discussed the difficulties, really which L is appropriate and which R is appropriate for our problem, then the thought is basically, why not just let the data to tell us which one is appropriate? So instead of doing some explicit specification of this regularization, what we do is that we make this projection directly, or this proximal operation directly trainable based on data. So here is a simple example where if you are going to approach, let's say, a least square problem, I'm not going to delve into the details here. Another family idea is that called a plug and play, which is kind of similar to the previous idea, which basically saying, if you have some intuitive method and what these guys are doing, for example, let's imagine that I'm trying to denoise an image. Okay, so why is my noisy image? And probably this forward model is just an additive noise model. I X plus some noise. So I have some data fitting term. Now the regularization, well, probably you tell me I want to make sure the image is sparse in the gradient domain, which basically boils down to the total variation regularization, or other things. But anyway, so we know that for denoising, this kind of operation typically tends to make the image more clear, right? Then the thought is basically, okay, so once we understand what's happening physically, why not just replace this this kind of operation by some explicit denoiser? Okay, so, and yet another family idea is it's called deep generative models, where the idea is that, if we think about, especially, for example, images, natural images, there's always a hypothesis in computer vision or image processing that natural images lie on manifolds, right? They are not random. They lie on some highly structured surface in high-dimensional space. So if we have a huge image data set, why not try to learn that manifold first? Then if your job is to reconstruct some images, then try to restrict that object to be in the range of that manifold. Okay, so that's basically the idea. So let's try to represent every image as generated by some nonlinear generator. G theta is a generator, and some seed. The manifold way of thinking about this is basically this is the low dimensional representation, and this mapping is going to map you to a manifold. Okay. I mean, if you are familiar with differential geometry, this is like you try to learn some charts for your manifold. And once you learn this generator, and you are trying to approach a new problem, you just specify your visual object as generated with some unknown input, where the unknown input is the thing you are trying to figure out. Oh, by the way, so if you guys have any questions, just feel free to jump in and ask. I just want to play this more informally. So there's nice survey papers summarizing all these things. Again, I'm much less comprehensive than the survey papers. I especially highly recommend this survey paper written in 2020 Although I should say a major limitation of this survey paper is the focus is on linear inverse problems where the model is linear. But in terms of the coverage, I think this one is probably the most comprehensive one. And just now we discussed about the middle way, which is less radical and which is actually very popular nowadays, I think, either in computer vision or in image processing or related field. But the common problems about this kind of approaches, again, is that how do you construct sufficiently large data set? And for algorithm unrolling or plug and play, another tricky thing is that people find it's not the case that you can play that with arbitrary algorithm. They found, for one particular problem, they found maybe when they plug that kind of ideas into projected gradient, it works. But when they plug that into other algorithm for the same problem, it doesn't quite work well. So it's actually sensitive to what algorithm you use. And also another interesting thing that we observed by applying this kind of idea to, for example, retrieval, which is a nonlinear inverse problem, is we observe that that kind of algorithm unrolling kind of idea, or plug and play kind of idea, is actually sensitive to the initial point you choose. For nonlinear inverse problem, we really worry about the non-convexity in general because there's no guarantee we can have a good initialization for the non-convex opening problem. But unfortunately, this deep learning, this integration of deep learning and a traditional formulation or traditional numerical method doesn't get rid of that requirement. So if you don't have a good initialization by whatever means, you probably are not going to get a good result there. So, or in other words, the way to think about these kind of unrolling ideas, or in general, these middle way ideas, is that they probably are only doing some refinement, provided you have good enough initialization. Instead of like they can really solve your problem if you don't have good solution before. And yet another way, another kind of radical way, I would say this, but this is on the other extreme, is what I'm going to talk about today is called a deep image prior. So what is deep image prior? The idea is actually pretty similar to the deep generative models I talked about just now. So for the object of interest, for example, image, I would think of that as generated by some generator and some seed. Okay, so here the generator is typically the deep neural network, and the seed is a vector or a matrix or whatever. So this is the way I'm going to characterize, or I'm going to parameterize my visual object, but I don't have any training data here. Okay, so this is only for this particular instance of the problem. I don't have any pre-training process for this. Okay, so what I'm going to do is that I'm going to just plug in this parameterization of the visual objects and form a new formulation from the traditional regularized data fitting formulation. Okay, so I start from here. I basically arrive at here. Basically, I just replace, whenever I see X, I replace that with a neural network with some stuff from random seed. And if you recall, we talked about deep generative model before. Deep generative model is still largely a data-driven approach where you should have some pre-training procedure to learn this generator, and then after you have learned it, you start to plug in. But deep image prior is single instance in this sense because we don't have this procedure. We don't have this learning procedure. So you just start from random weights, and you are just going to learn the weights over the operation process. Okay, so that's the big difference. And this idea, looks like a very innocent idea. This is very naive, but actually people have applied this to a lot of problems. nonlinear inverse problems, especially, and seeing a lot of successes. Just to give you some ideas, the wide range of successes we have seen, from simple image processing task, denoising in painting super resolution, to, for example, slightly more complicated image processing task, blind deblurring, and even more complicated MI reconstruction. This is a linear inverse problem, of course. And surface reconstruction, this has to do with image-based rendering and also dense surface reconstruction from point cloud in computer vision. Phase retrieval, which is a problem our group has been working on a lot, which is a nonlinear inverse problem, and many others. Actually, people have applied similar ideas to domains beyond computer vision or image processing. People have applied that to, for example, time series and audio denoising and structure. So I think this paper basically provides a very good summary of recent development around these kind of ideas. Another thing that's related to DIP, which I call it the cousin of DIP, is something that's also interesting. So this one is similar to DIP in the sense that you try to parameterize your object as some product of deep neural network. Okay, this is similar in this sense, but different than DIP. This one would think of the object interest as a continuous function. For example, if we have an image on R2, we can think that's a continuous function on R2, right? And the way you get your image, your image as a matrix is basically you think that as a continuous function, and then you do some discretization of the function on some uniform grid, and you get a discrete image. So this family of idea in computer vision is called neural implicit regularization. But I'm sure that some of you guys have probably come from applied math background, especially numerical PDE background. People have other names in applied math domain. It's called a physics-informed neural network, which is basically the same idea. So in physics-informed neural network, because we are trying to solve some PDEs using deep learning, we basically parameterize the PDEs using neural networks, because neural network in universal approximation theorem can, if it's sufficiently parameterized, can in principle represent arbitrary functions sufficiently well, right? So these are just the same thing, but the different domains call them differently. So this thing right now is super popular in computer vision. People have been using this kind of idea to do, for example, image-based rendering. So image-based rendering is where you basically take many images of the same 3D scene from different angles, and then you try to reconstruct in very tiny detailed way of the 3D objects of the 3D scene. So the basic idea is basically you try to represent by using the neural implicit representation, is that you try to characterize your object as a function, as a continuous function. So this function have 5 inputs. Yeah, you can imagine X, Y, Z. These are the 3D position, and the theta and the phi here. These are the angles. These are the 3D angles. Okay, so this corresponds to different angles to take pictures about the 3D scene. And then your regression is going to, the output from this function is going to give you the RGB values of this scene. Okay. So after you can reconstruct this 3D scene, you can generate some novel views of the scene, and which have a lot of computer graphic applications. Of course, that's why this thing is very popular right now in computer vision. So now we're going to talk about technical stuff. So, these are very powerful ideas, but actually there are also a lot of issues around these ideas. A significant issue is overfitting. So what do I mean by that? So practically what you can observe is that especially if your measurement have noise, if your Y contains some noise, which is quite common, of course. If you run this kind of idea, DIP, either DIP or the neural implicit representation, you typically see these kind of curves. If you measure the quality of the reconstruction in any way. So this one is a simple example for denoising, where we have a noisy image and we try to reconstruct a clean image. Okay, so if you start to run this thing, the DIP idea, you observe that initially you get a sharper and sharper images, but up to a certain point, the image quality start to degrade, and you start to see the effect noise coming in. This is what I mean by overfitting. This kind of overfitting is different from the typical overfitting that machine learning guys are talking about. This is not only for denoising. This is almost universal for all other applications of DIP and similarly for the neural implicit representation. So this is one big issue, and there are other issues. For example, overall, this kind of process also take like thousands of iterations, which is slow. I mean, typically, if you want to denoise an image, it take a few minutes, depending on the hardware, of course. And yet another issue is that practically the model also matters. So which kind of neural net model you should pick to make sure that you can do good reconstruction. This is also largely open. The choice right now is largely just us instead of any science or any principled ways. So this talk, I'm going to touch on at least two aspects. One is how to deal with the first issue where we see overfitting, and another thing I want to talk about is I want to show how powerful this family idea can be if you carefully apply it. I'm going to take a recent example we worked out on blind image deblurring. So if we have extra time, I'm going to quickly talk about a work that's still ongoing about how to substantially speed up this thing. Okay, so before I switch to technical things, any questions?
Yeah, I do have some question to clarify.
Yes, go ahead.
One slide you mentioned you don't need a lot of training data, right?
Right. So basically, I would say this is zero training data.
But you still need what kind of thing you need, right? You still need the y and a z, right? What is that in like?
Oh, so we still need the y because the y is the observation itself.
Okay, y like your measurement.
Yeah, we need to have y. We need to have f. F is the measurement model.
Okay, and you learn this g, theta, and z.
Actually, it's typically people just set z as a random thing and just fix it. Typically, people won't optimize z. People just optimize with respect to theta.
Okay, I got that.
Okay.
Thanks.
Sure. Any other questions before we move on?
Just along Yang question. So for this y, you have one y, you have a huge amount of the y.
We only have one y. So it's like we want to denote a single image. This y will be just a single image. So again, the difference compared to a lot of other approaches is there's basically no training data at all. You only deal with a single instance.
But then for a new image I need to denoise, you have to retrain everything, or you don't?
Yes, you do. Yes.
Oh, you have to retrain. Okay.
Yes. So yeah, I know that's why people complain about we are subject to the same problem as the traditional iterative method, right? You have to rerun this thing every time you see a new instance. Yes.
This is just to replace the total variation by something else.
Yeah, that's actually a good way of thinking about that. That's why this thing is called a deep image prior. You can think in this way. Okay, total variation, we can think that as one kind of prior for natural images, right? This one is another kind of prior. So yeah, I think that's a very good way of thinking about that. Yes.
But computation might be much harder than Because this is a neural network, you have to do the stochastic stuff much harder than variation.
Right, you can do stochastic, although here you don't have to because you only have a single instance, right?
Oh, I
Typically,
see.
people do stochastic because they have a large training set.
So the parameter size here may not be very big as well.
Yeah, that's a good question. Actually, the original DIP, the number parameter is larger than the number of pixels in the image.
Okay.
So
Okay.
it is big. It is big. But
Okay.
the amazing thing is this. The amazing thing is that if you have a nonlinear inverse problem, if you write down this natural formulation, some problem you will find if you run, for example, gradient descent, you'll find like a bad local minima. That's entirely possible, right? Because your operation problem is non-convex in general, right? But what's amazing about this thing is that after you do this kind of reparametrization, you can think of this as a reparametrization, basically. You actually get far better solutions. That's amazing.
Interesting.
Yeah.
But how about noise, right? Because your L is fixed. Let's say L2, then you have to you can only handle Gaussian, which you may or may not know the noise distribution. You still naively plug in the Gaussian.
Right. So yeah, this doesn't totally get rid of the difficulty about choosing the right L. Yes, of course. Yeah.
Okay.
Yeah.
Okay.
Mm-hmm.
So there's some kind of overparametrization of the prior, so therefore the quality may decay as you show.
Yes. Yeah. Exactly. Yes.
I see. Okay.
Yeah.
Thanks.
Mm-hmm.
I have a question.
Yeah. Go ahead.
Okay. I'm looking. Can you go back to your previous slide?
Yeah.
So are you learning the generative model, right? Basically, you're learning the G, the parameter theta for G.
Right.
So basically, you are not, in computer vision, we can also, why you learn? I just, this is different, right? You try to solve, right? So the first, you during the testing, what are you doing? Are you trying to just solve the optimization problem?
There's no training or testing. There's no concept of that because this is not supervised learning in principle.
So during the testing, you basically solve an optimization.
Yes, exactly. So this, again, there's no training stage at all. What you do is direct text, basically.
No, So basically, during the testing, you're solving the optimization without using any neural networks, right?
Oh, there's neural network. This is the neural network you are doing.
No, but that is the generative model. G is the generative model.
Oh, no. So, okay. So, again, there's no separate training stage at all. So the way to think about this, I think probably a less confusing way to think about this is just traditionally we are doing this, right? And now I do a reparametrization of my objects. That's it. So basically we just arrive at this problem. So forget about like a data-driven approach. This is not data-driven approach.
But I saw your minimization is over the theta. The theta is.
It is over the theta. So we don't have training data, but yeah, we have a neural network. Yes. But yeah, I think a better way, per the previous question, a better way to think about it is we have a prior that my object can be parameterized.
Yeah. I'm just a little bit confused because it looks like you're trying to learn the parameter for G, which G is the prior model, right?
Yeah. I mean, you can think of this as generator, but actually it's arguable whether this is a generator or not. Right? Because you are only learning from a single image, right?
So why don't you just, for example, you learn another model that just predict the X from Y?
Predict the X from Y?
Yes, subject
to
the prior. Yeah.
You mean the first approach I described, right?
Oh, you have first approach.
I think you're talking about this approach, right?
No. I'm talking about you basically you learn you have a generative model that gives you the prior, right? Prior about the 3D information right. Then you have another neural network, kind of like a regression.
Oh, you are talking about the neural implicit regression.
Yeah, something like
yeah. Yep.
So that means you're going to learn both the forward model to predict X.
Oh no. So yeah, this one is also single instance. So here the object you are interested in is actually this whole 3D object. So this whole set of observation is about the same object. So this one, we shouldn't think of this as constructing a data set. This is not a data set. This is like your observation consists of this whole collection of 2D images, because your object X is just this 3D scene.
Okay. Right?
Anyway, so this is also single instance. There's no training procedure at all.
Okay.
Yeah.
Thank you.
Mm-hmm.
So G, can I?
Yeah, go ahead. Yeah.
Sorry, can I clarify another thing? So, because as you mentioned, right? So you have the in the inverse problem point of view, right? You have the eopose problem, but it decomposes mapping to be F composed with G theta, which becomes even more eopose. What's the magic here?
Well, I don't know whether it's even more eopose. I mean, I mean, you definitely make the problem like
harder
from operation point of view, you probably make it more complicated. Yes, I agree. Yes, but I mean, if you there are multiple intuitions here. One intuition is that if you have read some theoretical paper of deep learning, why people think in deep learning we can do successful optimization. Some of the theory there is saying it's exactly because of the overparametrization in deep learning, in deep neural network. So, because if we think about typical non-convex problem, yes, I mean, you have a high chance of getting some bad local minima, right? But the theory basically saying if you sufficiently overparameterize the neural network, then very likely you are going to find actually very good local minima. That's probably very close to a global minima. So this is one prevailing theory about deep learning in general. So that kind of intuition can be applied here also, in terms of optimization, I would say. We do observe this, by the way. I mean, for example, phase retrieval, if you just write down a natural, say, least square formulation for that, you repeat 1,000 times, probably you won't ever find a good solution. But once we do this kind of overparameterization, just parameterize in this way, we get a very good chance of finding a good solution. So that's from operation perspective. From prior perspective, you can think this as imposing another kind of prior on the visual object. So that's why I emphasize, it's not arbitrary G theta will work. Actually, practically, people need to choose some particular architecture to make it work. For example, for images, people would typically take some convolutional architecture.
Sure.
So actually, there are some theoretical papers explaining why convolution matters here. So.
Okay. Thanks.
Mm-hmm. Any other questions before we move on? I mean, when I first see this, by the way, we didn't invent this idea. This idea was invented by some computer vision folks. But when I initially saw these ideas, I also felt like shocked, basically. But these are very, very powerful. Practically, after we work out several projects, I'm very convinced that this is helping us to make progress on very hard inverse problems. Okay, so the first thing about the overfitting issue, we have a couple of papers, although this one is more recent and more lightweight. I would definitely recommend this technique for doing early stopping. So just now, actually, some of you already asked the question and actually already got the right intuition why we have this strange issue where initially we learn something clean and then the quality started to degrade. So if you run some quick test for, let's say, you just do a regression of an image, okay? But just imagine this guy's identity, and we just trying to regress against a given image. And let's say the target you are trying to regress against, one is a clean image, the other one is a random noise. This one is just a noisy, totally random noise. And if you look at the operation trajectory, you see this typical trends like this. Okay, so how to interpret this? This is saying somehow, if we parameterize this guy as a neural network, especially convolutional network, you'll see that this kind of thing learn natural images way faster than learning noise. Okay, so this is an empirical observation. What this implies? Well, if you have noise and clean image together, this thing is going to pick up the clean content first, and then that basically explains this part, right? It's going to pick up the clean part first because initially it mostly learn nothing about noise. And later on, if you continue to run it, because practically people are using very powerful network here, so that it's so powerful that you can basically fit everything. So if you continue to run it, the noise start to kick in, and that's why the performance start to degrade, and you see the noise come in. So of course, this is not a theoretical explanation. There are some theory there for some simplified model of this, but empirically, this is evident if you run this kind of experiment. Now, the problem is how to solve this. In the literature, there are several families of ideas. The first family of ideas, of course, come to mind is that why not just do some regularization, right? Whenever we have some noise, we want to avoid noise, we can try to do some regularization. So that basically means there are two families of ideas. First family of ideas are, we think the neural network is too powerful. Let's try to control the capacity of neural network. Another family is why not just throw in more prior information about the object you are interested in. For example, adding total variation regularization for images, for example. But unfortunately, the tricky thing is that whenever you have regularization, the regularization parameters depend on the noise level. So here I show a simple, quick example. You just need to pay attention to the red curves. So the top row here is showing, for low-level noise, for these different kind of ideas for doing the regularization, you almost get rid of the overfitting, right? You still see a little bit, but it's not severe. But for the same set of parameter, if we move to high-level noise, then the overfitting is still there and it's significant. So that means it is tricky to find the right regularization level. So this is probably not that universal solution. Another family of ideas is trying to model the noise. And from modeling the noise, we try to design something to get rid of the overfitting. I'm going to just quickly talk about two representative examples. One of the examples is called DOP, double overparametrization, where they only deal with the case where the noise is sparse noise. And the way to deal with that is that they parameterize the sparse noise by this particular parameterization where in the literature, people have shown that if you parameterize the object in this way, combined with certain optimization procedure, you tend to get some sparse solution at the end of the day. That means this guy tends to be sparse. But of course, as you can imagine, this is very, very specific for sparse noise only. And of course, if you have other type of noise, for example, Gaussian noise, people have also tried to derive some kind of divergence kind of regularization to regularize Gaussian noise. So, this kind of ideas, they are successful for that particular kind of noise, but the difficulty is really how to extend this kind of idea for other noises, especially practically, we may not know the noise model, right? And we may not know the noise model, we may not know the noise level also. So it's tricky to get this work in general. Another family of idea is saying, okay, so we are going to have, that kind of bell-shaped curve, right? Then why not just stop at the top point? Well, of course, this is very natural to think about. But the thing is that, okay, so the curves we plot, these are reference-based image quality metrics. That means we need to know the ground truth to see the curves, but practically we don't have access to a ground truth, right? If we have access to a ground truth, then the problem is already solved. Why we want to do that? So practically we don't have access to that kind of curves. But you still want to do early stopping. You want to stop roughly around the peak performance point. How to do that? Well, there's some ideas in the literature also. I won't dig into the details, but it's basically subject to the similar kind of limitation like the previous approach I talked about. They are very specific for particular type of noise. They are also very specific for particular noise level. So I kind of doubt whether this is really solving practical problems. If you have that kind of limitation. We actually propose a very simple approach. Actually, you can ignore this one because this is the first paper, but I wouldn't recommend the method there because this one is very involved. I would actually recommend this one because this one is very simple, surprisingly simple. How surprisingly simple? Well, basically what we do here is that we keep track of the running variance of the intermediate reconstruction. Okay, so what I have here, the blue curve is the PSNR curve for image denoising, for one particular instance of image denoising. And this red curve is a running variance of this intermediate reconstruction. So you can see actually the peak of this have a rough alignment with the value of this. Okay, so of course this is a purely empirical observation, but actually we use this to try to detect the peak, and it works amazingly well. And actually we have two variants, and you don't need to get the details here, but roughly speaking, the idea is just to do some running average estimation and then try to stop whenever you detect significant change in the curvature. Okay. And the method we described here actually have very, very little overhead compared to the DIP itself. That means, which is ideal because you don't want this thing to be too heavy to run together with DIP itself. So I said, this is purely based on empirical observation, but actually you can derive some theoretical backup for this. I'm not going to tell the details of the theorems. These are based on like some significant oversimplified version of the problem. But somehow, these two theorems roughly saying that the variance, the running variance of the intermediate reconstruction roughly should be curves that lie below these two bounds. Okay, so especially the upper bound does, exhibit this kind of curve, this kind of shape where you have a value to detect. Okay, but I just want to clarify this is not complete. This is just some partial understanding there. And this, again, this idea is very simple, very lightweight, but it works amazingly well. Actually, this works across different noise types. We test on 4 different types of noise and different levels of noise. Okay, so the average detection gap, by detection gap, I really mean the actual true peak PSNR and the PSNR we detect. The typical gap is only around 1 PSNR point. Okay, but there are some occasional outliers, but these are like very, very rare. The typical values are just less than one PSNR point. And this also works amazingly well on real-world images. We take some large-scale, I think this one is around 1,000 images, real-world images, for denoising challenges. The detection gap is roughly around the same level. And by the way, we don't tune our parameter there. Actually, we only have 2 parameters. We don't tune the parameter across the experiment. And this is also effective on more advanced tasks. For example, MI reconstruction. This is a relatively more complicated linear inverse problem. It's similarly effective. The detection gap is similar. And also some nonlinear problems. This one is for blind image deblurring, which I'm going to talk about in the second section. All right, so before I move to this session, any quick questions? All right, then I'm going to move to this one. Blind image deblurring, this is a classic problem in computer vision and image processing. So the mathematical model for this is that we have observed some blurry and noisy image, which come from some convolution of some blurry kernel with some clean image and with some additive noise then. And from computer vision perspective, most of the blurring come from motion, either the relative motion of the camera and the image, sorry, I should say the scene, or it could be defocus due to significant variation in the depth in the scene. The general problem, people tend to call it blind deconvolution because, it's not really only for image deblurring. You see a lot of application of this general version of this problem in different scientific domains. For example, analysis of microscopic images. There are a sequence of landmark surveys about this problem. Again, this is a super classic problem. So, we have all these surveys describing the success over the past 2 decades. I'm not going to repeat all this because, it's pretty dense development there. And if you're interested in this topic, you can check out this GitHub repository also, where, these guys actually have up-to-date summarization of progress there. But in any case, especially after 2015, the field, this blind image deblurring field, have significant shift to data-driven approach, as you can imagine. But actually, if you check out recent surveys that basically is focused on deep learning-based solution, they all claim or they all point out this significant problem about obtaining sufficiently expressive data. So again, I comment on this before, for simple inverse problem, especially for linear inverse problem, probably you can collect data by, real world collection or by simulation. But for these nonlinear inverse problems, you have a lot of constraints by collecting this kind of data, even by simulation, because there are a lot of things you can simulate there. And there are 3 significant practical issues around the state-of-the-art method for blind image deblurring. The first one, the significant one, is that actually, practically, we don't know the size of the kernel. So almost all the previous approaches, they assume they know the kernel size. Another thing is that they normally only test on like very low noise level and Gaussian noise, or probably some complicated noise, but again, low noise level. But practical image, especially in low light environments, the noise can be substantial. And another aspect is that what if you simultaneously have these 2, or maybe you only have noise, but somehow you are using your method you're using a deblurring method to try to solve that noise only problem. I call it model stability. So if you do a simple test with significant over-specified kernel size, because practically we don't know the kernel size, and also noise, you can see a lot of them will simply fail with a lot of artifact. These are all the state-of-the-art methods for BID. So the idea here is we are going to apply DIP idea for this problem, but we have 2 visual objects here. We have the kernel, we have the image. So what I'm going to do here is that we are going to have 2 groups of DIP. So that's why I call it double DIP. This idea is actually not new. It's recently published in CVPR and other places. But somehow this prior work still subject to the same problem I talk about, the 3 practical issues. And what we are doing here is basically try to carefully customize and modify these things to make sure they can solve the 3 practical issues. the first group of modification is about how do you specify the size of the kernel and the images. As I said, practically we don't know the size of the kernel. So it turns out using DIP, we can actually be very, very aggressive in specify the size of the kernel. We actually specify the size of the kernel as half the size of the image in both directions. So that's pretty aggressive. And similarly, you can overspec the image according to convolution law. I'm not going to elaborate on that. Another thing is that people typically take the total variation kind of regression on the images. But what we found is that this thing is super sensitive to the noise level, which is probably common in image processing when you apply total variation kind of regulation. So what we found is that if you use the normalized variant, L1 divided by L2 variant, actually the parameter is much less sensitive. Okay. And another important thing we have to modify is which architecture to choose. This is another factor whenever you apply DIP kind of idea. What we found is that actually it's not a good idea to use DIP to represent the kernel. Okay, so the image itself is fine. The kernel, the property is very different from natural images. Instead, the best way to represent the kernel is something come from the neural implicit regularization. This siren is a particular version of that. Okay, so this is directly using a neural network to represent the kernel instead of the output of the neural network as the kernel. And they have very different kind of spectral properties compared to DIP. And early stopping, I already mentioned it. It's crucial. We apply the early stopping to make sure that we don't do overfitting, especially the noise can be substantial here. And also model stability. I'm only going to compare our prior work, the work we built on this thing called self-deblur versus ours. So you can see that when you have both, they still have a lot of artifacts. But after our careful modification of the method, actually we get much sharper images compared to theirs. And also we evaluate on real-world data. In the real-world data, the most challenging cases are cases where the lighting environment is the ambient light is very low. And also when you have like large variation in the depths of the image. These are the difficult cases. So on these difficult cases, we are doing much better than previous approaches, actually including some data-driven approach. So actually this one, this deblur again, and this one, these are data-driven approach. That means these are actually trained on massive amount of training data and then doing the prediction. All right, so that's about blind deconvolution, and I don't think I get time to talk about this last thing. Any questions about the second part? Okay, so if not, I can quickly close this up. So basically, I think I talk about two things to address two practical issues around DIP. One is about how to do early stopping. So basically, compared to other ideas where we do regularization, we do careful modeling of noise, or we do other kind of early stopping. The method we propose, which is very simple but very effective, actually is successful, across the easy and the difficult tasks. And also, I show you a powerful application of the double DIP idea to this blind image deblurring task, which we actually make it work in a very new regime where you have substantial noise and also substantial kernel overspecification. And I bypass this one. This one, the random projector is basically to address the speed issue in DIP, and actually that one we managed to speed up, I think, by roughly, I think on average is 20 times. So if you're interested in this work, you are welcome to check out the papers, except for the last paper, which is near completion. All the other papers are archived. You are welcome to check out and give us feedback. Otherwise, thank you very much for your questions and attention.
Okay, thanks a lot for the very interesting talk.
Sure, thank you.